Okay, so today we are going to understand that how we can use LSTM for the next word prediction from a given text data or any node data or the text data, I can say, and how we can use custom embedding layer and what are the parameters required for the custom embedding layer, and we'll try to understand the meaning of that custom embedding layer, that how we can use that on any different scenarios. And the secondary thing, today we will develop a sense that what exactly the tokenizer and what exactly the model, and the tokenizer and model both we will use why when we start using a pre-trained generative AI models, when we try to download that, so we'll have to download the tokenizer and the models both. And today when I will show you one on Hugging Face, one very famous model which is called T5 architecture based by the Google Flan T5. So there are multiple models others. I'll show that. So now let's start it with the beginning. So here we are just importing the data, sorry, packages, NumPy. No, no, it is not pre-processing, but I'll show you. I'll show you. Let us see. So here just we are importing the necessary libraries from the Keras. This is tokenizer. Two categorical, if you remember, it is just to convert into encoding part. So how two categorical works, I showed it yesterday also. Today also I'll show. This is the sequential to create a sequential model object. This is to create a dense layer. This is for the LSTM layer. And this is the today new is the embedding layer. How we will use the embedding layer. And this is the NumPy. Okay. And now this is our data. So Jack and Jill went up the hill to fetch a pail of water. So this is our data. Embedding, I'll come on that. So what exactly the embedding is? Okay, let me tell you that what exactly the embedding mean. So hmm, 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 correct. Yeah. Hmm. Okay. So let's suppose this is the word here, sentence here. Hello, how are you? So before, let's suppose our task is that whenever we will give this input to the model, it should predict this, and when we give this input to the model, it should predict this, and so on. Now we might observe that we are feeding this text to the model, but actually this raw text is not going to feed inside the model or the algorithm. It needs to be converted into the numerical form. So there are multiple way to convert this into a numerical form or a vector. So the first is here one hot encoding, which we saw it yesterday. So what exactly the one hot encoding? So and then there are multiple. So there is an something called TF-IDF also. That also I'll show you that what exactly the TF-IDF. And then after there is an something called word to vector. Okay. And then there is an something called we can use some custom embedding. Okay. which we will use it today. So what exactly the custom embedding is, we'll understand. So embedding, for now, in a simpler and layman way, you can understand it is a numerical representations of the words or the text. So let's suppose I'm representing this hello like this: 0 0.2, 0 0.3, 0 0.4, and 0.6. So this is just, these are the some features to represent the hello. Now what exactly the meaning of that? Let's suppose there is a word which is called apple, and now I have to represent the apple in a two-dimension words. Two-dimension means there are two um, number values. So one is 0.7 and one is 0.1. So this is the one feature of the apple, and this is the other feature of apple. Let us suppose the first part here is 0.7 is the technology part, TCH, and this second part is here the taste part. So definitely, if apple is being used in terms of the technology, then this technology, this one, this part will be always higher. But if this apple will get used in terms of the eatable items or the fruits like that, so this part, this one, the taste part will be higher and this one will be the lower. So how these things get calculated? For that there are some neural network, and with that it get calculated. So for that the one is word to wake, how it get calculated. Okay, now one hot encoding and the TF-IDF. This is just, they were using some statistical formula or some basic formula to calculate that. One hot encoding is simply what exactly it does. Let's suppose you have the text here with too many lines, 10, 100. So first it will take all the unique words from this. So the unique word here, let's suppose something is hello, how, are. This is the unique word from the text which has in 4 lines or something. So just an hypothetically understand hello. Now how would you represent the hello? So if in the first line, if in first line hello is available, so for that I'll make hello as a 1 and rest all as a 0. So this is the representation for the hello. Now how do you represent? How this one will be 0, this is 1, this is the 0. So now you can see the every word is getting represented into the number. So this is how you will represent the entire your word into the this number, or you can say the vector. So this is how the one hot encoding works. But TF-IDF, they have improved. Why? Because the reason, let us suppose you have the unique words of like 10,000 in your data. Sorry, 10,000 in your data. So here 10,000 unique words or the columns are there from 0 to 999. Now let's suppose you are representing a word education in the first line, and let's suppose the education is coming at somewhere at this 700 index. So here it will be 1, and rest the entire row will be 0. So you can see how sparse it is. There is a no point to processing this entire thing with only one value and rest all are 0. So it was not giving the actual meaning, the semantic meaning of this. So that's why they improved a little bit with the TF-IDF. Okay, and then after, TF-IDF was also very too much static. It was not getting changed with the context. I will come on a very depth with the TF-IDF especially. And then they used a neural network based algorithm to create the vector, to create the embedding for every words, and that is the word to wake. And there is an other also which is called glove. And this is again, we are using the custom embedding layer, so we do not need a separate neural network to train it for the custom embeddings. We can use this embedding layer in our LSTM or our neural network, where we are trying to predict the next word or the next character or the sentiment, and that itself will automatically convert into the a vector. Okay, but it doesn't mean this. What is this? First, this hello is there, no? So you need to convert into a number. So hello will, let's suppose, represented by 200. How is it getting represented by 121? R is getting represented by 76. U is getting represented by 89. And now this 200, this index, let's suppose this is an index number, and this one will, by the custom embedding layer, will get converted into the vector. Now what should be the vector dimension, that we will see. The same way this 121 will be. So if suppose this is a 100 dimension, this one hello word is getting represented, then how will also getting represented into 100 dimension. This R will also, and this U will also get represented by this dimension. Okay, so this is how the custom embedding works. So am I making sense a little bit at least? Embedding in, embedding for what? Benefit of embedding is, so the first is the, like, you cannot pass the, understand the text. So for that we converted into the number. Let's suppose every text got converted into, so I'm coming on that. So if suppose 76, 121, 89, 32. Now I am saying, is this 76, is this 76 has any information about this one or this one? No, it doesn't have. So what I'm saying, and when we converted this into a one hot in yesterday class, so 0 0 0, let's suppose this is 1 and then 0 0. So in this also there is a no any semantic information for this word with relation of this or this. There is a no relation. So is it a possible that I will make a relation this one with this one, or this one with this one? Is it possible I can create some vector which is somehow relatable to this, somehow relatable to this? So that is the embedding. That is the main use of them. Correct. No, see, it won't usually in embeddings. When you're embedding, it doesn't understand the meaning. It doesn't take the meaning. It takes the it's a relation. It's but how it is coming, how frequently it is coming together, that it try to understand. So let us suppose I'll give you, you have a 10,000 records, let's suppose, and in 10,000, uh 900 times you have used how with R, and then 100 times you have used how was your health, like that. Okay, so now, and if you train the model for a next word prediction, and if you'll pass the word how, there could be a 90% of the chance that the next word it will predict are, in spite of predicting is. Okay, more. So that is the embedding. That is not a dynamic. So that is, yes. So this error or this problem was actually solved in the attention. When I will explain this transformers or attention, no, this problem was actually solved by the attention. That was the issue with the embedding. But currently, just understand, this embedding try to give you the vector which will tell you the relation between the words of that sentence. Okay, so this is our data, right? So I've taken a very small data just to understand. So you can scale it up on any data. You can take it from the Kaggle or any public domain. Now here, see, here I have imported this tokenizer from the Keras pre-processing. Now I'm creating an object for the tokenizer, and here what I'm doing, lower equals to true, means automatically it will do for the every words in a lower case. So I'm not trying to generate a different tokens value for a same word with the different cases like upper or lower. Okay, so lower equals to, and then from this tokenizer there is a function fit on text, and then I'm passing my data in a list. Okay, see this here. And now from this tokenizer, there is a function called text to sequences. So when I will use that, you can see it has converted into an encoded vector. You can see this entire data got converted into this. Now, if you want, sorry, now if you want to, sorry, yes, correct, correct. And here it is also doing the same. You can see now, if you want to see what exactly this 2 is here, so from the same tokenizer I will use, and there is an uh, class method is called index word, and I will write get 1. So if here it is 1, it means what it is has given, and you can see this is and. Now you can see the 2. If I will put here 2, so it should give jack. See this. So now, right now, it has just converted every word into some specific number, which was stored in where? In this model, tokenizer model, for my data, right? Means this tokenizer model, now I'm fitting on my data, whatever I have the data. Yes, you can understand it as a label encoder as well. This is same as that. Just it is giving the uh, it will assign a unique index or unique number for every token. Yeah, it can be any number. It can be any number. It there is a no rule in that why it is giving this specific number. It can give any number. As per my knowledge, there is no rule that why it has taken this one. Okay, so it will take any number. Okay, any number it can give. Yes, yes. So this is the documentation. What are the available things available? Like see in that the parameter. So in tokenizer, what you can pass the number of words, how much number of words. Filter. If you want to filter, so currently it is filtering the special characters. Okay. So if you want to give that no, I want to include the special character as well. You can pass it here. Okay. Lower equals to true means currently make it lower, and currently it is splitting on basis of space. You can change the split also. Character level is false. Now it is because it is on word level. If you pass character level equals to, now it will do on the character level, not on the word level. OOV is called out of vocabulary. So out of vocabulary, I will just cover and address it at the end. What exactly the out of vocabulary? Okay, and analyzer. Let me check what exactly the analyzer. Customer to split the text. The default is text to word sequence. Okay, I mean, analyzer is just to, I think, text to word something it is saying. I need to check on the analyzer part, but this is how it is doing. Okay, now is it clear till here? No confusion. Now now we need to calculate the total vocabulary size. So total vocabulary size, how to calculate? This is a tokenizer dot word index. So how much the word index are there? Index is this one. Okay, and so I'm taking the length. So vocab size is actually, we have to take always, if suppose we have the vocab size is 20, you have to always take one more than that. Okay, so this is the rule in that network it you usually follow. So if suppose your unique words are 21, so it is taking 22. So if you can see here, it is sequentially it has taken from 1 to so I think basically it has taken on basis of the alpha I mean alphabetically order. So it has started with a and a, so that's why it has kept it as a 1. And then if you'll see here jack, it has when it has taken as a 2, so here it is 2, and wherever the jack will come, it will taken it as a 2. Okay, So this is how it has done. Now this is, so here now what we are trying to do, we have to predict the next word. So next word means we will create a list in which the two words I will put in a one list, Jack and Zill, then Zill went up, like this. Okay, like that. So for that I'm using this sequence, you can see it here. Now you will understand it here. 2 and 1, 2 and 1 is what, see this, 2 and 1, Jack and, then 1 3, you can see the next is 1 3, then 3 4, see that 1 3, then 3 4, then 4 5, then 5 6, see this 4 5 and 5 6. So two words I'm taking just to predicting the next, right? So I have just converted into that, and then I'm just converting into a numpy array. See this one will get, it will show you like this. Okay, okay. Now here I'm just checking the shape. So how much sequence was it? So total 24, and with the column 2, because in every records I'm taking 2. Now I'm converting into x and y. So what will be the x here? This, the first column is x and this second column is y. So you can see here, all row from the first column, all row from the second column. And if you want to just see here, so x of 1 is 1. See this, x of 1, sorry, x of, let's put 0, the first record, let me show 2. See, this is 2, and the y of 0 is probably the next one of that is 1. So here, this is same, the x of 1 is 1, and y of 1 is 3, like that. Okay, so for every word that it will learn about the, train it for the next word. Understand? And now here I'm just trying to convert into a categorical. If you remember, the yesterday we have done it for the y number of classes. So y will become 24 records were there, and now the column will become 22. Understand? Here like this. Now this y will somehow look like this. See this. It is now representation in 20 total. Vocab size was 22. So in 22 classes it will look like. See this. This is the one. Okay, like that. Now here we have created a sequential object, correct? Now this is important, we need to understand the custom embedding layer. Now here I'm adding, so this is the new, we haven't read it in last class, yesterday class. So model.add and embedding I have imported on top. So the first parameter in embedding layer, you have to pass the vocab size. We have which stored this here vocab size, if you remember, this is the vocab size. Okay, 22. Now the second parameter which you are seeing, the 10 here, it means that for every word what should be the dimension, in and what dimension you want to represent your word. So if you remember this one, when I was explaining it, see here, this is when I was saying it, this every word in how much dimension you want to represent. So I said here 10 means now in every word will be represented by the 10 vectors value. Okay, so there will be 10 values for the every word it will create. Like just yes, yes, like see here the entire sequence you will understand. If suppose I'm writing hello and how, so this is my x and this is my y. Okay, so I'm passing this one. If suppose in my embedding layer, so first it has converted into some index value, let's suppose that is 3. Now in embedding layer I'm saying that represent into the vector of dimension 10. So there, or let's suppose I'm just giving it here 4 in a 4 dimension. So it will be 0 0.3, 0 0.2, 0 0.01, 0 0.7. So this is the representation vector of that it will create. Okay. Now the same way it will go for the, and now input length. So this input length is exactly you have to pass in every row how many words are there. So in our case, how many words are there in every row? Only one, because this is the y, right? This is y here. This is only one row. In x, if you will check, see that x, if you are checking in every row how many words are there? One. So that's why I'm passing here input length is 1. So this is the 3 parameters you need to pass. Okay. 10 is 10, 10 is the representation of your word in vector. I will see. Suppose you want to see, I'll tell. First, understand. If suppose we are doing it one hot encoding, so what is the process? So it will take here, hello, how are you? These are the unique word. And now I want to represent the word hello. Okay. So what it will do? 1, 0, 0, 0. So what is the vector size of this? 4. Correct. This has the vector size 4. 1, 2, 3, 4. It depends on the unique, and it depends on the unique value. But now here what I'm trying to do, I'm just creating a random value between 0 to 1, between 0 to 1 of dimension 4, whatever number you will pass in that embedding layer. So in our case we have passed 10, but for example here I'm saying it 4. So it will take the random value from 0 to 1. So this is the minimum and the maximum value, like 0 0.1, 0 0.2, 0 0.7, 0 0.4, and it will get adjusted according to your loss in a back propagation, these values. Okay. So these are the hello के लिए, this is the word which is going at the first time, then the whatever the word, the next word will go, for that it will be created again the new, for the third word it will again create the new, for the fourth word again it will create the new. This, no, for every word there will be vectors, different vectors for the every word with dimension 4. that is that is not a probability, just understand it that these are the weights. Right now understand these are the weights. You will understand that how this value is getting created once you understand the completely word to wake. Okay, I will explain in the next class first word to wake, but right now just understand it only here, that every word is getting represented into some vector of this dimension, and this dimension which we are passing into the embedding layer. In our case we are passing 10. Okay, this every word will get converted into the vectors, every word. No, see, yesterday we were creating it the in a beginning, we were not doing it in our neural network. Now here we are using a neural network. Yesterday what we were trying to do, we were not trying to, we were just using 0 1 1 0 like that. If you remember, we were doing it like this. We were not creating some embedding vectors, embedding values for the every word, but today we are doing that. So this one will be, sorry, let me show you. Okay, let me show you. See this. what exactly it is. These are the only numbers. First time what I'm saying, today also we are doing the numbers. See, this is for every word or every text or every character we are creating the numbers here. Okay, now see what I'm trying to do here. If I'll print the sequence, what exactly this is, these are all the same, this number representation. I'm just converting the every text with that number. That's only. Is there any vector representation? I have shown it yesterday for any word. You can see here. Okay, okay, let me show. See, this is, so this is this again, these are just a combined, all these are the numbers only, these are not. Now today what I'm saying, this character 12, or just understand today in our case this is a word, and now this 12 will be represented into one vector. This is like this. Now in this single, yesterday only this 12 was going, but now today this 12 will get converted into the vector. So that's what it is doing it here. So if you will see from the embedding layer what dimension it is coming, you can see here 1 to 10 means every input word, because input length I have given here 1, and the output dimension is 10. Okay, and how many total records were there? 22. I mean records as in what I can say, the words which was going. So 22. So 22. So 22 into 10. This vocab size was actually 22. So 22 into 10. So how many trainable parameters are there? 220. Because if you will see here, you can relate it with this value. I am saying that total unique words or vocab size is 22. So total 22 words. Okay, unique words. Now let's suppose the word start with how and it ends with something is, like just in case. Now this word is getting represented into the vector size of 10, and this is total 22 words. This is total 22 words. For one word there are 10 trainable parameters. So for the 22 words, how much it will be? 22 into 10, 220. So that's what I said. Now here I am using trainable parameter. This one will get trained. This I can use anything. I'm saying I can use take 4. That won't be any issues. That's a yes. Higher the dimension, better the performance. Yeah, yeah, computationally it will take more. So we will see in a generative AI task that the for every word dimension in word to way Google has created 512, 1024 like that dimensions. And better the dimension it will capture, and why the better I'm saying, if the dimension is higher it will be better, you will understand when I will entirely explain the word to way. Yes, just understand, if I have to represent a word apple. Now apple can be written in millions of way. Okay, so if suppose I have a vector for a apple which has the dimension of 1024, it means I have used apple in 1024 different ways with the some features, with 1024 different features. Like apple can be used in a tech, apple can be used in a fruit, or maybe apple can be used in a juice like apple juice, like that apple can be used in some different. So these are the how this dimension means. Okay, so we will see it slowly. Okay, in embedding it will be clear. In the next class now I will cover the embedding. Okay, and then after here I'm using this LSTM layer. in that LSTM 75. Now just understand one thing here, uh, which is very important now to understand this architecture actually. Suppose my x data is x dot shape. So what is, let's take the actual value. What is x dot shape in our scenario? 24 by 1. So here nothing, it means it is 1. Okay. So if suppose x dot shape is 24 by 1. Okay. Now what does it mean? So it means that embedding layer will take each word. Okay. Each word from the rows. So the first time from the first row. So 24 is the here total row. Okay. And one column, only one. Okay. And 24 is the total row. So it will take embedding from and convert into the vector. Convert into dense vector. Yes. One second. Let me check how much it is. It is 24. See this. This 24. No. It is. Let's see. This vocab sizes. So here we are creating a 2 no. That's why it has increased. See this. Pair of 2 we are taking. So every time this 1 is getting common, no, so that's why the 2 has increased. Understand the point? 2 1 1 3 3 4 4 5 like that. Because what I'm doing, so I have just prepared it. Yes, because I'm taking the previous word and need to predict the next word. Yes, Jack and then and Zill like this. And Zill, then Zill went up the like that. Okay. So this is how. Now if if so the first time if suppose we have x shape is 24 by 1, it means that the first time the first this first row and the first word will go first time. This is from 24 row one column. So here understand it one by. That is total 24 row and one word. So this is one column. Okay. So the first time this first row and one word, this one will go in embedding layer. Okay. And it will go as an input. It will go as an input and it will get converted. It will get converted into like this. So let us suppose I'm representing in dimension 10. So how it will get converted? 1 comma 1 and 10, because the first record is getting converted and the first word getting converted in the dimension of 10, and so on. If we have the multiple, then it will get increases, keep on increasing. So this is now, and this one will fade into the LSTM. And I said it, no, LSTM, if suppose you have taken a unit 75, so the output of the LSTM will be 1 cross 75. Okay, because if you have taken a unit is 75, then output will be the 75. You can see it here. See, this is, I have taken it 75, so the output is, see this. And now why this much of training parameters? Because yesterday I showed, no, those many neural networks were there. Sorry. No, no, this is not only the 220 into 75. This 220, how it came, I already explained. Now, how this 25,800 is coming, because every time a vector of 10 dimension, a vector of dimension 10, this is if you suppose LSTM, so this is the xt. So xt is what? Xt is a vector of dimension 10 is getting inputted. Now here ct is there, this ct minus 1, ht minus 1, and they are one neural network, two, three neural networks are there, and I'm saying there are total 75 units, 75 units. So this 75, this 75, this 25, 150, and this one will be also 10 10 vector. So this is the 20. So this entire it will multiply that many of parameters it should get trained. Okay, so that is why this is the value it is coming here. Yes, the number of neural network. Yes, normal neurons in each neural network is 25. So this is, and the finally in our output layer we have to give, if suppose we have a next word prediction, so how many unique words, so that is the vocab size I have passed, and the activation is the softmax, because it will give the probability for each word, and whichever word probability would be higher, that it will final as an output. And then I'm compiling the model again, the same. Now everything is categorical cross entropy, because it's a multi-class classification. Optimizer Adam I'm using, you can use any RMS properties on accuracy, and this is the model summary. And then I'm fitting the model here with the 200 epoch with x and y. So you can see here the result is finally 87% it is coming accuracy. Okay, and now let's understand how we can generate the next sequence. So if you will see here, I have just created a new method, generate sequence, and it is taking two things, model, tokenizer, and cd text is the input text. Just understand whatever the input text you are passing in words means how many words you want to predict the next. Okay, so here I'm just creating a loop. Suppose I want to create a predict 6 words after my input word. So now see the tokenizer, from the text input, whatever the text you will give first, it will tokenize that. So what it will do, it will create a unique number which had already created. Whatever the number was present in that tokenizer, no, that only it will take. Now let us suppose you have trained this tokenizer, and in which you had only a word hello, how are you, and now while prediction you had given a word education, then it will not able to understand that. It will say that I haven't seen that word education, and it will give you the empty vector, it will not give you anything, and at the end it will throw error. Okay, so here, so this is why the large language models, they use the entire internet data, Wikipedia data, all the publicly available data, so that the any of the words should not get missed. And for that also they were using some algorithm which is called word piece or sentence piece, WP is the name of that algorithm, to handle any kind of token. So that is an advance, again we will see in a Gen AI when we will start that those models. So first it is just encoding your input into, and that I'm converting into array, and then from model I'm predicting the probability, and whatever the probability will be higher, that class it will predict here. That's it. And now just see here I'm passing, sorry, yhat is just a variable, that y hat we usually we use it as an our predicted value. Okay, you can use any, that is not required. So y hat I'm using. Okay, and again see what I'm doing here, if that word is available, if that word and index, so I'm saying if that index is equal to yhat, then what it will do, it will see in outward has taken an empty, in that I will add that word. So what exactly it is doing, it is just trying to keep on add the word in the string, and keep on giving the next word that it is doing. You can see it here. Let me print where exactly. See this generate sequence. Here I'm passing model, the tokenizer from the top, and the word I'm passing jack, and how many word I want? Five, let's suppose, and now let's run. See this jack and zil went up the. So since we are using it as on the same training data, that's why it is giving you the good result. Now let's suppose I have given here, it is, see this, no, when I used here jack, and what it has predicted, five words, one, two, sorry. Yes, so that's what it is taking. So when I give here jack, it has taken it from the beginning because it has not generated. No, because see here, when you will see this jack, here also it is. But before that there wasn't something. No, that's why it has taken it from here. Okay. Now let's see. I'll tell. Let's put here jack fail. Okay. Let's put here jack fail. Okay, so yeah, because we have trained it on the single word. Now see here, this word has, it is not there in the tokenizer. That's why it has thrown this error. Now let me put this fail only. See this fell down and Jill went up. Now it understood. So it will take only those words which are available in the tokenizer. Okay. So now this is the problem with the small models. This is called the out of vocabulary problem, because in your tokenizer vocabulary only some words were available, but while using that model, while predicting the model, the words which you are using, that was not available in the tokenizer. Because of that, it was throwing the error. So these to solve these problems, the language models use some algorithm. Okay, first thing, they train it on the use data. Rarely you will pass some word, and if suppose you are passing, so there is an algorithm which handles those. Okay, so which we will see, there's a technique called sub tokenizer. So they use that, they breaks the words into characters in a different, and then combine that. So this is how it works. Okay. Yes, but if still, if some word you passed which it has not seen in future, so there isn't some technique they use so that it can handle any kind of word that it will build. No, I'll show you, let me. So I had prepared one ppt for when I gave a presentation. I'll show you. You can see it. I just do not want to go depth in that, but I'll show you. You can understand it here. So you can see my screen, right? You can see there is a sentence called where can I find pizzeria. So what it will do, the words which are frequent, no, it will not do anything with that. But see that word pizzeria, what it will do? It will divide as Pizzera. Okay, it will divide like this. Now the vocabulary will be created like this. Now if suppose you have a word, now the new word will come, let's suppose list area. So definitely the list would be in its vocabulary, and eria it will again separate it out, and eria it will take it from here. See this eria completely, it will take it from here. And this is the how it creates the vocabulary. You can see the byte pair encoding. This is the algorithm. Okay, there is one more algorithm they use, so we will see that how it can be solved. Okay, in depth. Okay, just allow me, let me